Good afternoon. This is the first segment of section 2.4 and 2.5. Typically, there's only maybe one or possibly two examples that come out of section 2.5 that I like to cover. So basically, the most of the material that's left in chapter 2 is what's in 2.4. There are some majorly important kinds of ideas that are going on here. That are sort of separate ideas, and I may break them up that way and then finish off the section with some very specific examples. But some of this has to do with material that maybe you have previously seen in a physical science class, like a chemistry or a physics course, but it has to do with measurement, accuracy, and precision, and certainly that's not generally the main focus of a math course, but it's something that is emphasized enough in this textbook that I think it is valuable to talk about, and also probably something that's reasonable to expect a person to be able to perform on a test. We have been talking about, well, to start with, I'd like to talk about what are called significant digits. Sometimes that term is interchangeably used with significant figures. Both of those terms I have heard before. But anyways, let me kind of give you some pictorial ideas and try to describe what's meant by significant digits with some examples. So let me just come over here real quickly. Okay, so this is section 2.4, and again, we'll cover 2.4 and 2.5 in the same section. There's not enough in 2.5 to justify its complete thing. So, what's a significant digit? I'm just going to discuss this. I'm not going to really write very much here, so a significant digit specifically refers to values, numerical values that are derived from measurement of some kind. And generally speaking, when you study this in a physical science class, there are two kinds of operations that are considered. One is when you're adding two numbers together, and one is when you're multiplying two numbers together. And unfortunately, neither one of those is really great for estimating errors in indirectly measured quantities, things that, you have a measurement and you do something with those to calculate a new sort of measured quantity, like, for example, area. It's length times width of a rectangular area. But if the length and the width both have errors, how accurate can the area be? Those kinds of questions. So I want to pose it this way. Typically, what I will describe to students is that the distance of my house to the campus. So when I get in my car and drive to the campus, it is roughly 7.2 miles from my house to the parking lot. Okay, and then from the parking lot to the front door is maybe 245 feet. So the question then is, based on those measurements, how accurately do I really know the distance from my house to the front door of the ST building? And it would be crazy to think that somehow taking a number that is fairly inaccurate, right? Something that's to the 10th of a mile, right? 7.2 miles, a tenth of a mile is like 500 feet. So the number could be anywhere between 7.15 miles and 7.25 miles, which is a spread of 500 feet worth, and then tack on to that this 245 feet, which is smaller than the error in the other number. To think that somehow I've improved the accuracy of the answer just by adding them and keeping those extra digits is kind of nuts. So here's how we handle significant digits when it comes to addition. So let's kind of compare those things. And I'll use the same units because when I describe the process with miles and feet, sometimes a little bit confusion. But let's say that we had used some kind of a wheel, a rotating wheel to measure the distance of the length of a road. And maybe you've seen these before. They kind of go around in a circle, and every time they make a complete loop, there's a ticker on them that goes 1, 2, 3, and you can reset it. They're used sometimes for transmission lines or power poles, that sort of thing, where there's a certain amount of cabling that needs to be used, and it's used in construction purposes and other sorts of things as well. But let's say that we have one that's a meter roller, so it'll roll out a meter. And let's say that we measure a distance from like one street corner to another, and we come up with this distance of let's say what seems like a good number. How about 124 meters? And then, so that was from one point to another, like maybe say the length of a sidewalk or something. And then from that sidewalk, we use a tape measure to measure a distance from the end point of the sidewalk to maybe say like a manhole or something. And because I'm using a more accurate device, a tape measure, I can measure probably down to a centimeter without too much trouble. So then maybe this extra distance is, let's say, 2.34 meters or 234 centimeters, about a little bit over 6 feet. So the question is that if I wanted to, in some sense, add these two numbers together, right, the result, what is the result? Well, okay, so first off, I think what we need to understand about this number here is that it is accurate to a meter, right? The digit of significance is sitting right here before the decimal point, right? The last digit of significance. So this, anytime we're doing a measurement, this distance is not just 124. What it is it says the actual distance, say D, is somewhere between half a unit below and half a unit above. It may be inclusive. Generally speaking, we will include the lower bound. So it'd be 123.5 meters and up to, but not including 124.5 meters. So when you make a measurement, and this is how it's recorded, this is what it really means. It means the true measurement, the true distance is somewhere between these two numbers. And similarly with this other one, let's maybe call that D1, D2 is somewhere between, on the low side, 2.335 meters, and on the high side, 2.345 meters. So hopefully it's clear that this is a tighter range, right? There's only a difference of a centimeter here, but there's as much as a meter here. So there's a lot of leeway. So the rule for significant digits when you're doing addition is to say, and we could do this sort of longhand. So 124 plus 2.34. When I add these up, I'm going to get 126.34 meters. So, all right, mathematically, this is true. When you add 124 to 2.34, you're going to get 126.34. Now, that does not take into account the fact that these numbers are themselves somewhat inaccurate, right? They don't represent an exact number, but actually a range. So the rule for adding numbers that have measurement is to take the least accurate number, and that would be, in this case, 124, and its digit of significance controls the digit of significance of the addition. All right, So this is the mathematical answer, but when we apply this significant digits rule, the actual answer will be 126 meters. Okay, now it seems like we lost a whole bunch in here, and that is true. But because the distance of 124 has such a large range, these extra little bits really don't contribute very much. Okay, so 126 meters would be the recorded answer. Pretty much every problem in this text that involves a measurement will now apply these rules of significant digits in some fashion or another. It's a little bit screwy. Anyways, this is how distance works. For multiplication, when you're multiplying two numbers together, it's not about the positioning of those significant digits, but how many of them are there. So what does it mean for a digit to be significant? It means that it's not necessarily a placeholder, but is in fact a number that's derived from measurement. So for example, in this situation, that has 3 digits of significance: the hundreds position, the tens position, and the units position. The other distance also has 3 digits of significance. But just to kind of make some comparisons, I'd like to look at what would be the difference between these 3 numbers. And let's say 124.00. Now, I guess in some sense, these are all the same number. From a mathematical standpoint, they're exactly equal. But with this number, it actually corresponds to a range from 123.5 to 124.5, whereas this number ranges from 123.95 to 124.05. Right. So here the range is a meter. Here it's 10 centimeters, and with this one, it'll be 123.995 to 124.005. Somewhere in there is the range. This only has a range of a centimeter. So by counting these up, this has 3 significant digits, this has 4, and this has 5. That usually is okay and easy to tell when the decimal point doesn't create some sort of ambiguity. So let's look at maybe a different number. How about 190? And the question then is, how many digits of significance does that have? Well, there's some ambiguity there. You don't really know, because the question is that last digit something that was measured, or is that last digit just a placeholder? It really comes down to a question of whether or not the number was, it depends on the accuracy of the device being used to make the measurement. So for example, if you wanted to say that that digit is just a placeholder and not a significant digit, this is the way you would write it. On the other hand, if it was a digit of significance, it's often customary to either put a period, which now indicates that this is a number of 3 significant digits, or alternatively, you could do something with a bar. But that, again, is only because of its position with respect to the decimal point. If we took a number that was, say, a little bit bigger, maybe has several zeros, this number has 2 significant digits. However, this number has 3. And that bar is used to indicate, which of these zeros is actually significant. This is not a super complicated idea, but it is something that comes up in one of the problems very early on in this section involving the height of Mount Everest and the measurement. So this notation is not typically used in the book, but it's something that you may see at some point in your future career. There may be other alternatives for trying to describe how that works, but when it comes to multiplication, the key is to count up the number of digits, right? It's not about their position with respect to the decimal place, but actually how many digits there are. So what do we do with them? Well, when we try to multiply two numbers together, so just take, for example, let's see, 2.4, we're on page 2. So let's say that we're trying to calculate an area. And on one side, let's say it's kind of a skinny sort of thing, skinny, really more rectangular than square. And let's say that on one side, it is measured as, let's say 14 meters. And on the other, sort of the base and the height, let's say, is 124 meters. Okay, so then the question is, what's the area of this rectangular surface? So the area is going to be equal to 14 meters times 124 meters. This is there's nothing unusual about this. This is just mathematically multiply base times height. So 14 times 124, we get 1,736 square meters. Don't forget these units. The units are important. But now the rule for significant digits is if this calculation involves a multiplication, that the way to interpret the accuracy of the numbers is to count up the number of significant digits. So this number has 14 meters has 2 significant digits. 124 meters has 3 significant digits. Well, you can't take a more accurate number and multiply it by a less accurate number and end up with a more accurate result. Okay. Notice this final number here actually has 4 significant digits. So you had something that was, good to, some amount, something that's a little more accurate percentage-wise, and then something that's like super accurate, which is just, it doesn't make any sense. So the rule is to take the least number of significant digits of all things that are being multiplied together, 2 and 3, the smaller number is 2, and apply a rounding rule to the result. So the answer for the area is 1,700 square meters, something that has 2 significant digits, because our our least accurate number in the original calculation, or the original measurements, only had 2. So this is a correct application of significant digits. Now, I'm going to tell you my personal opinion about these because they work for, they're reasonably close for things involving addition and things involving multiplication. Now, most people will then try to extend this to talk about trigonometric functions, or how square roots work and things like that. So consider for a minute what kind of calculations we do when we're involving triangles. So we have, for example, we sometimes use the Pythagorean theorem, right? C squared equal to A squared plus B squared. So if I have a number with a certain amount of significant digits and I'm squaring it, and then I have another number with a certain amount of significant digits and I'm squaring it, if I want to find the third length, the hypotenuse, I'm then going to take the square root. So C equal to positive square root of A squared plus B squared. So the question is this an addition? Is it a multiplication? What does the square root do? And I'm just gonna tell you that there's not really a hard, fast rule on how this is supposed to work. At least not from a significant digit standpoint. To be able to understand how to actually deal with error propagation is not an easy task. In general, you need to have access to partial differentiation, which is a topic talked about in a Calc 3 class. But what I will say is that in my observation of the answers that are to the problems in the text, what they will do almost always will be to treat all problems like their multiplication, right? So no matter what kind of an operation you do, square roots, adds, whatever else, they will just simply count up the number of significant digits. The minimum number from all the inputs will then be applied to the final result. and just say, okay, well, that's it. So for example, and this is maybe of some importance, let's say that you had measured an angle, and that angle was, let's say, 24 degrees, 3 minutes and 52 seconds. Okay, so the first, I'm just going to point two things out. First, these two things actually say the same thing, right? I put in this 0 for a very specific reason, and that has to do with these significant digits, because this minute part has two significant digits. So does the seconds. You don't see it if you're looking over here. You think, oh, well, that's only got, if you were to count this up and say, how many significant digits are in this measured quantity, you say 1, 2, 3, 4, 5. But you're skipping this placeholder that actually is significant, right? This is a more accurate, what you're really talking about, what is the accuracy of this number? So a degree, minute, second measurement has either 5, 6, or 7 significant digits. In this case, we have 6. So when I now use an angle that has 6 significant digits, and then I calculate a trig function using it, so it's like, what is sine of theta? Well, if I go to my calculator, and we've done this in the previous section, so 24, and it was 0352. Remember, I can't, for this calculator at least, I can't take trig functions directly of degrees, minutes, second, angles, so I'll need to convert. So I'll turn that into decimal degrees, and then I'm going to take the sine. Now, there's a number that has a lot of digits, and that kind of comes down to, well, what's the deal? So if I just mathematically compute that, I've got 0.407763912, and it keeps going forever. So the question is, from an observational standpoint, how do I apply significant digits? Well, here's what I will tell you, is that the book almost exclusively will just apply whatever the number of digits are with the input, and that's how many significant digits there should be on the output. So this thing should have 6 digits of significance. The input had 6, so the output should have 6. That means that the actual answer based on application of significant digits is 0.407764, right? And that's a unitless number. Now, I'm going to take, in this video may be getting a little long. So what I'm going to, but I do want to show you why this application of significant digits is a bunch of bull. And that is my personal opinion on it, based on based on experience as a physical scientist. It really does not. It's too simplistic. And I'm going to give you an example of how that works. So let's look at the angle 89 degrees, 89.9 degrees. Okay, so this represents, when it's made based on a measurement, this represents an angle somewhere between, on the low end, it could be 89.85, and on the high end, it could be 89.95. Right, so somewhere in between there is where the actual angle is. And if we were to take the tangent of theta, and I'll just do that real quickly, 89.9, take the tangent. Notice it's kind of a big number, 572.95722134, . So if I look at my number of significant digits on the angle, you would say that that my result, my computation from tangent, should have 1, 2, 3 significant digits. So the answer should be 573, whatever. It's unitless. So 573 should be the answer based on this sort of weird application of significant digits. So what does this represent? This represents a number that is somewhere between, on the low end, 572.5, and on the high end, 573.5. right? That's how you're supposed to interpret this. It has 3 significant digits, so it's half a unit up or half a unit down, right? But if that's the case, then these two intervals should correspond. I should have that the tangent of 89.85 should be roughly 572.5, and the tangent of 89.95 should be roughly 573.5. Well, let's just see what we get. The tangent of 89.85 degrees, so 89.85 degrees, take the tangent, is 381.9709908, etc. And going the other way, 89.95, take the tangent. So tangent of 89.95 equals 1,145.915299, etc. So based on this, that we're talking about a range of values between roughly 400 and 1100. How many significant digits does this number have in comparison, right? I mean, the answer is none. There are no significant digits. This number is so inaccurate. So that's why I just wanted to point out, don't be too taken in by this discussion about how to apply significant digits when you're dealing with trig functions. There is a rule. We're going to apply the rule. Generally speaking, when you're using sine and cosine, you don't have too much problems, but tangent gets particularly troublesome near 90 degrees and also at 270. So anyways, I just thought I would mention that, kind of build it up and then tear it down, because I think the way that that the over-reliance on significant digits in the physical science community, especially at the most entry levels, is gives people a false sense of how things work. So I thought I would bring that up. Next, in the next segment, we're gonna look at some sort of left-handed ideas, but you need to have at least a framework for how these significant digits business works before we can go on. So I'll see you in the next segment.